In this lesson, we'll look at tangent line approximations. Specifically, provided the derivative at a point x at some point x, how can we write the tangent line to the curve at that point and then use that tangent line to approximate function values near that point? So first, we'll look at how to write secant and tangent lines. For secant lines, we first need to calculate the slope of our secant line over an interval. Let's say the interval is a f of a and b f of b. So our slope of our secant line is just the average rate of change over that interval. So that's the first thing we do, is calculate our average rate of change. The next thing that we can do is use the point slope form of the equation of a line to write the equation of the secant line. So for this point we can use either for this part, we can either use a f of a or b f of b as our point of interest, since both of those points lie on our secant line. So we can write y minus f of a equals the slope of our secant line, again the average rate of change, times x minus a, or y minus f of b equals m secant times x minus b. So in a nutshell, we just have to calculate the average rate of change and then plug the average rate of change into the point slope form of a line for one of our 2 points of interest, either a f of a or b f of b. For tangent lines, okay, the logic is the same, except now instead of computing the slope of a secant line, we're calculating the slope of a tangent line at a specific point x equals c. So in order to calculate that slope, again, that's just a derivative, we calculate our derivative at point x equals c. So the slope of our tangent line is the derivative at x equals c. And then we do a similar step as we did with secant line. We use the point slope form now, except now we only have one point that we can use in our point slope form, c f of c. So we're going to have y minus f of c equals m tangent times x minus c. So we find our derivative at x equals c, and then we plug that into the point slope form for a line. Now our next thing that we're going to cover is how to approximate a function at a point using tangent lines. So let's say we're given some really complicated function, f. It may be a super complex function, or it may be a function we don't know yet because it's just a collection of data points. And suppose we want to make an approximation at some value close to some point x equals c. So it may be too complicated to actually find out what that function value actually is, but we can approximate what the function value is by taking note of the following. When we zoom in really close on x equals c, we see that our tangent line is approximately equal to the curve of our function f right here. Thus, if I want to approximate f of x naught, where x naught is some point close to x equals c, what I can take note of is that the corresponding point on the tangent line will be approximately equal to f of x naught. So what I can do is I can use my equation of the tangent line to find the value of my tangent line at x naught, and that will be approximately equal to the value of my curve f, the value of f of x naught. So what we do is we call a tangent line a linear approximation of f near x equals c, because we're using a tangent line to attain approximation of a function value at a point near x equals c, hence why we say linear approximation. So for example, if we have written the equation for a tangent line at x equals 4 for a curve f, we can write it as y minus 4 equals f prime of 4, the first derivative of x equals 4, times x minus 4. We can then approximate f of 4.2 by plugging in x equals 4.2 right here, and then solving the above equation for y, which in this case would just amount to the extremely difficult case of adding f of 4 to both sides. And thus, in that way, we can obtain an approximate value for what f of 4.2 is using a linear approximation. So in a nutshell, what we've seen so far is how to write the equation of a tangent line and then how to use the equation of a tangent line in order to add on to the, in order to approximate a function value at a point. And we can also use secant lines as well. With secant lines, it's the same logic, except now we just have the average rate of change plugged in right here instead of our derivative. So as with all approximations, there are going to be some errors. So how can we determine what type of errors we'll get, whether our approximation will be less than or greater than the actual function value? So we take note of the following right here. If f is concave up at a point like we have right here, okay, we notice that the tangent line is going to lie below our curve, while our secant line is going to lie above our curve. Thus, if a tangent line approximation is used, our approximation will be less than our function's actual value, while if a secant line approximation is used, the approximation will lie above and thus be greater than our actual value of the function at our point of interest. Likewise, if we look at a concave down region right here, we see that our tangent line lies above the curve, while our secant line lies below the curve. Thus, if our approximations occur over a concave down region, the tangent line approximation will be above and thus greater than our actual value of our function at a point of interest, while our secant line approximation will be less than the actual function value at our point of interest. We can summarize these with the results below in a nice little table for us to jot down. So if we use a tangent line approximation and our function is concave up, aka the second derivative is greater than 0, then our approximation will be less than the actual function value. While if we are concave down, again our second derivative is less than 0, our tangent line will be the tangent line approximation will be greater than our actual function value at this point. And then with a secant line approximation, if we are if we're concave up at a specific point, then our approximation will be greater than the actual function value. While if we're concave down, the function value, the approximation using a secant line will be less than actual function value. So you can see the tangent line and secant line do the opposite of each other. When a tangent line approximates one way, the secant line will approximate another way in terms of error analysis. So let's look at an example with a secant line, and then we'll do one with a tangent line. So let's write the equation of secant line for f of x equals square root of x over the interval 0 to 9, and then use the line to approximate f of x at 8.8, and determine if the approximation is greater than or less than the actual value of f of 8.8. So first thing we're going to do is calculate our average rate of change for our slope of secant line. So we're going to square root of 9 minus square root of 0 divided by 9 minus 0 is just equal 1/3. So now we can either use the point 0, 0, or 9, 3 to get the equation of secant line. We get the y values for our coordinates by just plugging in the x values into our function. So for x equals 0, y equals 0. For x equals 9, y will equal 3. So the equation of secant line is going to become y minus 0 equals 1/3 x minus 0, or just y equals 1/3 x, or y minus 3 equals 1/3 x minus 3, which reduces down to y equals 1/3 x. So again, you can use either point and you'll get the same equation of the secant line. Alright, so next we're going to move on to y equals 1/3 x. Okay, we're going to use that approximation we're going to use that secant line to get an approximation. So f of 8.8 is approximately going to be equal to, 1/3 of 8.8. We just plug x equals 8.8 in. And as a result, we get that f of 8.8 is about 2.933. Lastly, if we want to determine if this is an under or over approximation, we're going to need the secant line approximation. Or excuse me, yeah, just had a brain fart there. We're going to need the second derivative. So our first derivative of our square root function is going to be 1/2 x to negative 1/2. And then the second derivative will be negative 1/4 x to negative 3 over 2. So we plug in our point of interest to the second derivative here, and we're going to get negative 1/4 times 8.8 to negative 3 over 2. Now I don't know what 8.8 to negative 3 over 2 is, but I do know it will be a positive number, and I know a positive number multiplied by a negative number, in this case negative 1/4, will always give us something less than 0, a negative number. So because our second derivative is less than 0 at this point, the graph is concave down at x equals 8.8. So as a result, we're going to get that our secant line approximation is less than the actual value of our function at 8.8, so we get an under approximation. Write the equation of the tangent line for f of x at square root of x. So now we're going to do the same thing, but now we're going to apply it in reverse, and then we're going to apply it at x equals 9. So we take the first derivative, which is 1/2 x to negative 1/2, and we evaluate it at x equals 9. So we get 1 over 2 square root of 9, which equals 1/6. Using the point 9,3, we have as a result, using the point slope form, y minus 3 equals 1/6 times x minus 9. Simplifying this down a little bit will give us y minus 3 equals 1/6 x minus 3 over 2. Thus, we have our equation for the tangent line. So now we can use the equation for tangent line to approximate f of 8.8 by plugging in x equals 8.8 and solving for y. So we're going to have f of 8.8 minus 3 is approximately equal to 1/6 of 8.8 minus 3 over 2. I plug in x equals 8.8, and I replace y with f of 8.8 since that's what we're approximating, f of 8.8. So I add 3 to both sides, and I get f of 8.8 equals 8.8 divided by 6 minus 3 over 2 plus 3 equals 2.967, which I totally did in my head and not on a calculator. Beep, boop, beep. I'm a robot. So from example 1, now if we want to determine if this approximation is greater than or less than, from example 1, we know the second derivative is less than 0 at this point, so the graph is concave down at x equals 8.8. So as a result, our tangent line is going to lie above the curve at x equals 8.8, and thus the value that we've attained is going to be greater than the actual function value at 8.8, an over approximation. What's really interesting about this is the secant line and tangent line approximations can be used to obtain a lower bound and upper bound, or vice versa, for a function value at a specific point. So we got 2.933, which was an under approximation, and we got 2.967, which is an over approximation using secant tangent lines. So we know that f of 8.8 has to lie between 2.933 and 2.967. This is actually how Isaac Newton first applied linear approximations. Was he first used them to calculate square roots for non-whole number values. So obviously, in his time, he didn't have calculators, so this was a very useful technique that eluded many people before him. Lastly, we'll look briefly at the slope of a normal line, which you should have learned about in geometry or prior classes. If not, we'll cover it briefly here. So a normal line is defined as a line that is perpendicular to the tangent line of a curve at a point. It's very applicable in physics and higher level mathematics. So as a result, it is something worth going over. So the slope of a normal line is given by the following equation. It is the negative reciprocal of the slope of a tangent line at a point. Okay? So if we're interested in finding the slope of a normal line at a specific point, all we have to do is calculate our derivative at that specific point of interest and then take the negative reciprocal of that derivative in order to find the slope of our normal line. And this covers the very wide field of tangent line approximations.